Hey there and welcome to this explainer. Today we're doing something really cool. We're going to build a complete, super useful math toolkit from the ground up as we dive into the entire 6th grade ratios unit. You know, whether you realize it or not, the world around us is totally governed by these hidden relationships between quantities. I'm talking about the speed you travel on the highway, the money you earn per hour, or even the exact mix of ingredients in your absolute favorite dessert. By mastering the concept of ratios, we're unlocking this incredibly powerful way to understand, organize, and really manipulate those relationships.
Okay, let's dive into this with the problem you've likely faced in your very own kitchen. So imagine you have a pancake recipe. It calls for 2 cups of flour for every 1.5 cups of milk. That specific ratio makes the perfect, fluffy pancake. But, well, what happens when you suddenly need to feed a massive party of 20 people? If you just start guessing and throwing extra ingredients into the bowl, yeah, you're going to end up with a dense, rubbery disaster. There's no way around it. You need a reliable mathematical tool to scale that recipe up flawlessly.
So here is how we're going to build that toolkit today. Section 1 is what is a ratio. Section 2 covers equivalent ratios and scale factors. Section 3 is comparing with ratio tables. Section 4 explores real-world ratio applications. And finally, Section 5 takes us to ratios on the coordinate plane. Let's get started.
Section 1. What is a ratio?
So at its absolute core, a ratio is simply a comparison between 2 different quantities. It's really just looking at how one amount directly relates to another. For example, let's say you track your typing speed, and you find out you type 40 words for every 1 minute that passes. Boom! You've just identified a ratio. You are directly comparing the quantity of words typed to the quantity of minutes.
Now, what's really interesting about this slide is the flexibility of the math language here. You can actually write a ratio in 3 distinct ways, and they all mean the exact same thing mathematically. You can use words, simply stating 2 to 3. You can use a colon, writing it out as 2, 3. Or you can write it as a fraction, with the 2 over the 3. Depending on the problem you're trying to solve, you get to choose which format works best for your toolkit. How cool is that?
However, there are some totally unbreakable rules to this tool that we need to talk about. First and foremost, order matters immensely. If a question asks for the ratio of teeth to no teeth in, say, a silly cartoon drawing, you absolutely cannot give them the ratio of no teeth to teeth. Actually, scratch that. If you do, it completely flips the meaning of the relationship and you'll get it wrong. Secondly, just like the fractions they resemble, ratios can, and definitely should, be simplified to their lowest terms. So if a cafeteria sells 80 milks out of 100 total cartons, that initial ratio of 80 to 100 perfectly simplifies down to a much cleaner, easier to use 4 to 5.
Moving right along to Section 2, equivalent ratios and scale factors. Let's look at a really practical situation, like bike race training. Say our starting ratio is that Audrey bikes 4 miles in the exact same amount of time that Megan bikes 6 miles. But what if Audrey bikes 12 miles? How many can Megan bike in that same time? We can solve this step by step using a multiplier, which we call a scale factor. To get Audrey from 4 up to 12, we multiply by 3, right? Because they're working at constant rates, we must apply that exact same scale factor of 3 to Megan's side. So 6 multiplied by 3 gives us 18 miles.
So the crucial point is this. Equivalent ratios scale up or down at the exact same rate. Think of it like zooming in on a photograph on your phone. You have to expand the width and the height by the exact same multiplier, otherwise the image gets all weird and distorted. Ratios work the exact same way to maintain their proportional relationship.
All right, Section 3, comparing with ratio tables. Let's bring out the heavy machinery.
Let's bring back that pancake recipe from the start of our explainer. A ratio table is pretty much the perfect organizational tool for equivalent ratios. By listing out the cups of pancake mix on one side and the corresponding cups of water on the other, we essentially create a master cheat sheet. We can instantly see that for every 1 extra cup of mix, we add 1.5 cups of water. Whether you need 2, 3, or even 4 cups of mix, the table flawlessly organizes the math. It allows you to instantly scale the recipe to feed literally any size party without a second thought. It really is that easy.
And you know, ratio tables aren't just for scaling up recipes. They are absolutely vital for making comparisons, too. Imagine you have 2 different middle school grades participating in a point-earning competition. If they each have their own ratio tables tracking students to points, you can use those tables to compare their constant rate side by side. By finding a common number of students in both tables, you can instantly see which grade level is generating points at a faster rate. It's a total game changer for word problems.
Which brings us to Section 4, real-world ratio applications.
When real-world word problems get a little tricky, we use a brilliant visual tool called a tape diagram. Let's say Jenna and Becca are selling cookies. Jenna sells 4 boxes for every 3 boxes Becca sells. That's a 4-to-3 ratio, which we can represent visually as 4 blocks stacked above 3 blocks. Now, if we know they sold 35 boxes combined, we just count up our total blocks, which is 7. Then we simply divide that total 35 by 7, revealing that each individual tape block represents exactly 5 boxes of cookies. It's like a giant puzzle. It turns a complex, abstract word problem into a super simple visual one.
Honestly, no matter if you're figuring out the ratio of accessible parking spots in a giant 385-spot parking lot or splitting up a classroom bank account, you should always pause and ask these 3 organizing questions. What do I know? What do I need to know? And what information am I given about the comparison? Filtering any word problem through these 3 questions guarantees you pull the correct starting ratio for your tape diagram or your table. It saves so much headache for sure.
Okay, time for the master level of the toolkit. Section 5, Ratios on the Coordinate Plane.
Let's map out Margot's family road trip. We are given the starting ratio that they travel 50 miles every single hour. We can immediately organize this into a ratio table, just like we practiced. 1 hour is 50 miles, 2 hours is 100 miles, 3 hours is 150 miles. But rather than just staring at numbers in a chart, we can treat each row as an ordered pair, meaning an X and a Y coordinate.
And this brilliantly illustrates the ultimate connection in mathematical modeling. You can take the ordered pairs straight from your data table and plot those exact points directly onto the grid of a coordinate plane. The x-axis becomes the hours, and the y-axis becomes the miles. When you connect those dots, you get a straight, diagonal line shooting up and to the right, perfectly visualizing the constant rate of the car's speed. Because this relationship is so constant and reliable, we can actually summarize the entire table and graph into one clean, concrete algebraic equation. The miles traveled, which we'll call m, is simply equal to 50 multiplied by the hours, which we'll call h, so m equals 50h. With that single tool, you no longer need the table to find out how far they'll travel in 20 hours or even 50 hours, you just plug it right into the equation. Let's test this understanding real quick. If you were looking at the graph of Margot's road trip, and you put your finger on the plotted ordered pair of 420, what does that specifically represent in the real world? Any guesses?
Well, it translates perfectly back to our starting situation. The first number, the x value of 4, represents the time in hours. The second number, the y value of 200, represents the distance. So that single dot on the graph tells us the whole story. In 4 hours, the family will travel exactly 200 miles.
This quote from the source material really hits the nail on the head and perfectly summarizes our journey today. Ratios are not just fractions with colons, they are dynamic, real-world relationships. By moving from simple written comparisons to scale factors, then organizing them in tables, mapping them with tape diagrams, and finally writing equations and plotting them on graphs, you have built a robust, foolproof toolkit to interpret proportional relationships in multiple, highly effective ways. The whole shebang.
So, you now possess the mathematical toolkit to effortlessly scale up a pancake recipe for a massive crowd or map out the precise timing of a cross-country road trip. But you know what? This is just the beginning. Take a look around. From the gears on your bicycle to the pixels on the screen you're watching right now, what other invisible ratios are quietly governing the physical world around you at this very moment? Keep your eyes open, and I'll see you in the next explainer.